Alright. Hi everyone. My name is Pham, and today I'll be talking about the Fourier series, giving a brief introduction to the series and talking about some criteria of its convergence. It should be noted that before we get into it, we're going to be discussing some material that should be already covered from an undergraduate PDE class regarding uh, some basics of the Fourier series, and also an analysis class, because we'll be talking about some uniform convergence and continuity as well. So that being said, let's get into it. We're going to first get into some historical background on the formulation and intuition behind how the Fourier series were created, then head into some preliminary tools that will help set up for our main result, which is Feyer's theorem. Afterwards, we'll give the result and its proof of Feyer's theorem, and conclude with some discussion on the future studies of this subject. So let's begin. So starting off with some history, we're going to first go on talking about D'Alembert, Euler, and Bernoulli, who actually formulated the ideas of the Fourier series before Fourier by a few decades, where they were interested in examining the behavior and phenomena of a vibrating string after being plucked in a closed system. In 1747, D'Alembert formulated the wave equation, as we see here, to dictate and measure the displacement of the vibrating string at a given time and point in space. It would give the general solution for the homogeneous boundary conditions, where Bernoulli would go on to give a proposal for the solution of the wave equation under inhomogeneous boundary conditions. Now, from his proposal, notable figures like Euler would come to reject it due to the fact that he was concerned with whether or not the function was going to be uh, well represented in terms of the convergence of the series and also what happened at infinity, or whether or not the series was actually a function. All these were not well understood concepts at the time, and so there was a lot of skepticism. This would follow for the next few decades until their deaths, and they were not able to come up with a well sought after reason or conclusion, and that's why none of the papers on the Fourier series published from them. It wouldn't be until, of course, Fourier would come along and publish the series for the first time ever in history in the Analytical Theory of Heat in 1822, where he sought to study the heat propagation through a disk, which can be represented through what is now known as the Laplace equation. And I also studied and created the time-dependent heat equation given right here. Now, Fourier's ideas would not be well received due to the fact that he did not give that much justification or analysis or rigor when it came to supporting his ideas. But fortunately for us and him, in a way, his successors took upon his projects and ideas, such as Dirichlet and Fejer, and sought to develop the analytical foundations that support the series, especially its convergence, as with Fejer, who we will be talking about today. With that being said, let's get straight into developing some of the techniques that we're going to be using to support Fejer's ideas. So first, let's recall from our PDE class the Fourier series on R. For like any function that is integrable on negative pi to pi, the Fourier series of the function is given by this equation right here, where the Fourier series coefficients are given by a0, an, and bn, which are found by first assuming that each term can be integrated termwise. We're going to be multiplying each term by either 1, cosine, or sine n x, and using the orthogonality relations to see that all the terms vanish except for the case where n equals m. We won't be diving too much into this, of course, because there should already be knowledge that is known already. But we're going to call upon this when we go to deriving the complex series in the following slides here. But first, we need to develop some tools to do so. First, we'll sought after Euler's formula, which is obtained by considering the Taylor series expansion of e to the I n x. which is precisely going to recollect to be cosine nx plus I sine nx, where I here is the imaginary constant square root of -1. Going a little bit further, some very useful definitions will be the complex representations of cosine and sine given by these forms right here. Um, Along with this, we're going to be considering the orthogonality of the class of functions e to the ikx, where k is an integer, as the inner product of e to the inx and e to the imx, the conjugate, will be two results. They will be either 0 when n is not equal to m, and 2 pi when n equals to m, because this is exactly how we're going to find the coefficient, similar to how we did so for the real Fourier series. That being said, let's go ahead and formulate the complex series. We're going to again take f to be any integrable function over minus pi and pi, such that its representation in the complex form is given by this sum, going from n equals negative infinity to infinity of Cn e to the inx, where Cn is the coefficient found through using Euler's formula and the orthogonality of e to the inx. And also, if we apply the same methods and techniques to find a naught, an, and bn, we find Cn by multiplying both sides of the equation by e to the minus I and x, and then integrating over minus pi and pi, as follows. Now that we've developed the complex Fourier series, we're going to actually be using this in our proof for Fejer's theorem. But first, we also need to develop Fejer's notation to go along with it as well. And first, we're going to be considering the Fejer means, which call upon the previous representation, just the partial sum version. So let the partial sum of the complex series be as such. So S capital N of x will be the previous sum, but instead of going from negative infinity to infinity, it's going from negative to n. Then, if we take the arithmetic means of these partial sums, we'll get the Fejer means, given as 1 over n plus 1 times the sum of k equals 0 to n of sk of x. So this is really just, the regular arithmetic sum done with these partial sums. And what comes from this as well is we get a really fascinating object called the Fejer kernel, given by the Fejer means, just without the Fourier coefficients. And it turns out that using the geometric series and also the properties of trigonometric identities, we can derive a closed form of it in the form of 1 over n plus 1 times the square of sine of n plus 1x over 2 divided by sine of x over 2. Now it turns out that this kernel has 4 really interesting properties that we'll discuss shortly. But first, let's go over what it looks like on a graph. So here for you guys, I've provided a graph of F8, F15, and F23. As we can see, we can make some really interesting observations here. One observation I would like to note is that all of these kernels are going to be non-negative. And this is, of course, due to the fact that our previous closed form is a square. It's a square term, an even function. Also, the majority of the concentration or the area of the kernel seem to congregate around a band close to, centered at 0. And outside the band, as in these tails, they all seem to go to 0 relatively quickly. So these observations are going to be important to us because they can be generalized in the following slide here. So going through these properties, we of course are going to omit the majority of the technical details, but we'll give you guys intuition on how to reach that. Now for the first one, the non-negative property, it should be very clear. As from the previous slide and the closed form, we can see that since it's a quadratic square term, it will be a non-negative everywhere for Lx. The next property that we'll discuss is the convolution property. And it says that the Fejer means can be represented as the convolution of f and the Fejer kernel. Now, using the definition of the Fourier coefficient Cn, and also manipulating the summations, reindexing efficiently, you guys should eventually be able to uh, verify this result here. And similar for the normal property, as in 1 over 2 pi times the integral of the kernel over minus pi and pi will be precisely 1. Using the previous techniques for the previous property, and also the fact that e to the ikx is orthogonal, forms an orthogonal set. And lastly, to address the tail end phenomena, we have the tail end property, such that if we formally define it as for any delta in 0 and pi, where delta is going to be less than the absolute value of x, which is going to be less than or equal to pi, we'll have that the modulus of the kernel is bounded by 1 over n plus 1 times sine squared of delta over 2. And this should be relatively clear to see, as we go back to the closed form, the numerator is a sine function, which is going to be bounded above by 1. So we're just going to look for a bound of the denominator. Since delta is taken to be less than x, it is implied that 1 over sine of x over 2 is going to be less than 1 over sine of delta over 2. That's required. And if we take n to infinity, it should be clear that this will converge to 0 as such. With that being said, let's get right into Fejer's theorem, which proves the uniform convergence of certain functions' Fourier series. So, what does it say? So, under the criteria that f is a continuous function on the closed interval of minus pi and pi, and it's also 2 pi periodic, and it's also extended across the entirety of the real line, then the Fejer means of f will converge to f as n goes to infinity uniformly. Now, this is very powerful for us because uniform convergence is the strongest convergence criteria that we currently have in analysis. So if we're able to verify for certain f's that their Fourier series is convergent and uniformly convergent, it gives us a strong justification and confidence and means to look to use them in other applications. So let's get straight into the proof. So first, from our analysis, since we're proving uniform convergence, we're going to have some epsilon, and by definition limit, we're going to have some epsilon be greater than 0, such that we find some index j that is going to be less than or equal to n, such that the distance between the Fejer means and f become arbitrarily small, or less than some epsilon. Then, what we're going to do is we're going to use the convolution property and also the normal property to rewrite the distance of the Fejer means in f, such that we have this quantity right here. Using the triangle inequality, we're going to bring those absolute value bars inside, and using the non-negative property of the kernel, we're going to bring them closer in to zone in on this difference, the distance between f of x minus y and f of x. From here, we're going to draw upon our observations from our plot and analyze the function's behavior, or the integral's behavior, using the kernel's behavior around the band that is centered at x equals 0 and the tail ends as well. We're going to verify that analyzing the integral on those will send both to 0. Doing so, yeah, there we go. I1 will analyze inside the band, and I2 will analyze on the tail ends outside of the band. From our assumption that f is continuous on negative pi and pi, 2 pi periodic, and extended across the real line, we have from analysis the Cauchy-Schwarz theorem that f is bounded and thus uniformly continuous on the real line. But what does this really mean for us in technical terms? That means that I can find some real number b that bounds the entirety of f. And for all epsilon bigger than 0, there's going to be some delta such that the distance between x, y, and x minus y and x, is less than delta, implies that the distance between f of x minus y and f of x will be less than some epsilon over 2. This is very good for us because we can directly apply this to I1 automatically. As you can see here, I1 by, since f is bounded and uniformly continuous, we'll have that I1 is less than the integral of the kernel times epsilon over 2. Bringing that on the outside and taking this integral instead over the interval minus pi and pi, we can see that this term, this integral, will go to 1 due to the normal property, and we'll get our epsilon over 2 as needed. On the other hand, similarly, since f is bounded, we can say that f of x minus y and f of x are both bounded by b. Or in other words, I2 will be less than or equal to the integral of the kernel times 2b. Simplifying and bringing it out, we'll get that b over pi, this will be equal to b over pi times the integral of the kernel. But since by the property of the tail ends, we know that fn will converge to 0 for large enough n, so we can say that the integral also goes to 0 and get closer and closer to 0 arbitrarily, or be less than some pi epsilon over 2b. And simplifying this out, we'll get our desired epsilon over 2. So if we combine both the inequalities for I1 and I2 and take the extreme ends, we'll get that the distance between the Fejer means and f will be less than or equal to I1 plus I2, which will be less than epsilon, which is exactly what we're trying to show. With that being said, now that we've shown the uniform convergence of the Fejer mean, of the Fourier series to f for certain f that are continuous and 2 pi periodic over R, we can look to apply them now. We can go back to our PDE class and confidently apply such functions and solve them, solve the heat equation, for example, without questioning why we're able to do so. But this discussion regarding convergence is really the little tip in the iceberg. Why? Because there's multiple types of convergences. Even though we discussed the strongest one, there's still pointwise convergence, convergence in the mean space, and other Lebesgue spaces that are worthy to discuss, including the convergence of the Fourier coefficients themselves. Aside from that, we still haven't discussed other major things in Fourier analysis, such as the Fourier transform or the Riemann-Lebesgue measure or lemma, which sought to generalize integral properties as well. So hopefully hopefully those things interest you and causes you to do some more research. But for this presentation, I guess I will conclude it here, and with my acknowledgments as well. So thank you guys for listening, and I'll see you guys next time.